Okay, so we're continuing on with class 5. I did a little introduction in class 5 where we did the eigenvalues for three-dimensional stress. That's really just sort of an added thing into the topic, but instead we're mostly doing two fairly long and complicated stress problems, combined stress problems that include pressure vessels. So here's one actually out of Shigley. This is problem 3. It's problem 105 in chapter 3, and we have a thin-walled cylindrical steel storage tank that's 30 feet in diameter and 60 feet tall, is oriented with its longitudinal axis vertical. The tank is topped with a hemispherical steel dome, and the wall thickness of the tank and dome are 0.75 inches. If the tank is pressurized to 50 psi and contains water 55 feet above its base, and considering the weight of the tank, determine the maximum state of stress in the tank and the corresponding principal stresses, normal and shear. The weight density of water is 62.4 pounds per cubic foot. And the problem in the book doesn't show you what this looks like. You have to kind of like imagine it. But this is like the big idea, right? It's a tank. It's got a cylindrical, it's got a hemispherical dome on it. They told you it's 60 feet tall, but it's only got 55 feet of water into the thing. And it's got 30 feet, it's 30 feet diameter. That's not the diameter symbol, but I put it in there anyway. And it's got 50 psi of air inside up here, and then the thing is 3/4 of an inch everywhere. So there's a lot of stuff going on, and that's where life starts getting tough. This is like one of those word problems that we enjoyed so much when you were in. When did they introduce the word problem? 4th grade. Yeah, our lives are never quite as good as they were before we knew of the existence of the word problem. They probably have word problems in like kindergarten now, right? But anyway. So anyway, I was always afraid of the word problems, and now I became a professional word problem solver. But don't worry about it. We just had to pick the thing apart and draw a little picture. Oh man, drawing a little picture helps, right? So we draw this thing, and it looks kind of like a bullet right there, and it's got here's the little tank onto the top of the thing, and we know that it's full of water up to the 55 feet. I'll put a little pressure gauge at the top, beep, beep, and that pressure gauge tells me that there's air inside there of 50 psi, and those are psi G, by the way. It's always G, right? Unless they tell you otherwise, right? And we have there's a line right there. Here's our 55 feet of water. Here's our 60 feet of height. Diameter of the thing. Assume it's the outside diameter. Why not 30 feet? And we get, if we were going to try to draw this really thought that we would say that this is 0.75 inches thick right there, right? Something we might already know, that we have a 15 feet radius hemispherical tank. What else? Well, when we go to look at, we have to figure out where the maximum stress is going to be. And I'll give it to you. It's somewhere down here at the bottom edge, right there, at a point right there. And so we're going to go like, here's going to be Y. Am I going to do that correctly? And here is going to be X. So here, coming out of the page almost, is Z. Right there, right? So like the right-hand rule, there you go. X, Y, Z, right? There's Y, X, Z's coming at you. So we're going to look at a little guy, and it's going to be on the inside surface. Did I say that? Did I do mine for the inside surface? That's the thing I want to know. Yes, I did. All right. So we're going to look at and now we're going to think about all the kinds of stresses that are going to be there. It's a pressure vessel, right? So it's definitely going to have hoop stress, right? And if we want the worst case, hoop on the inside was worse than hoop on the outside. And it will have radial stress, right? Won't it? But that radial stress is going to be equal to whatever the pressure is at that point. We also have, so one thing, the water is going to get higher and higher pressure as we go down. But it starts out at 50 psi and it gets larger and larger and larger as we go down, just like when you go swimming and you go down. Hydrostatic pressure, right? But also, the tank weighs something. The tank weighs a thing, so just the weight of the thing alone is going to be causing stress onto the piece. Oh, and that's going to be tension. That's going to be compressive stress, won't it? Interesting. Wow, so that's a lot of stuff to do. So we have to be pretty organized. Let's start out with some geometry stuff. That's a good place to start with a lot of things. And we're going to need to know the weight of this tank, of the steel. Right. But let's just write out what we know. That's a good thing to do with word problems. Let's stick with inches, right? So 360 inches in diameter. That's 30 feet. So the outside radius is 180 inches. The inside diameter, we could subtract that out right there. I'll just do the numbers. You could do the 358.5 inches, right? You got to make sure you're subtracting 2 times the thickness. The thickness is 1.5, so subtract out 1.5 from 360, and you get this, right? So you have to go 2 times the thickness when there. Or you could have just subtracted the thickness from this, right? So that was 179.25. Right, subtracting out the 0.75. So then we want to know what is the ratio of the thickness to the radius. Well, if you do that, you find you have 0.004184, way less than 0.1. Therefore, this is a thin-walled approximation. It's totally fine, right? Some of the other information they told us that the weight density, or specific weight, if you will, is 62.4 pounds per cubic foot. Something else I have memorized, but maybe you don't. The specific weight of steel is 0.284 pounds per cubic inch. Good thing to know. Comes up a lot. How much steel weighs? And it's by cubic inch usually. It's just a good thing to know. I happen to memorize it. Okay, so we want to get the weight of the steel, right? So let's find the weight of the steel. So the way that we're going to do that is we're going to figure out the volume of the steel, and then we're going to multiply it by that weight density right there. And we want to do it in cubic inches. So we can, okay, I could look it up for the dome. So this is my symbol for volume right here of the dome. I looked that up somewhere and I found out for a half dome is 2/3 pi. Okay, yep. RO cubed minus RI cubed. I looked it up. And anyway, if we go ahead and put the 180 and the 179.25 in there, I don't need to write this out to fill it all in. 1.520 E5 cubic inches. And if we have the hair of the walls, that's going to be the area of the walls times the height of the walls, right? So it's going to be the 60 feet, aka what's 60 times 12? That's 720, I think, 720 inches. And the area right here is going to be pi over 4 do squared minus di squared. Don't know why I did the pi over 4. I could have done the radius, right? Times h, right? So if I put that diameter there and that diameter there, and I put 720 in here, we end up finding that we get 6.095 e to the 5 cubic inches. So we want the weight of the steel. We get this of steel times V dome plus, that's supposed to be dome, when V walls. And Lazy Man doesn't feel like writing this out, but this is 0.284, and these are these two numbers right here, and we end up coming that it is 2.163 E5 pounds. Whee! That's a lot. 216,000 pounds worth of steel. Wow. Now, something else I might want to get. Okay, so I might want to get, what is the pressure at the bottom of this tank, right? So the pressure at the bottom, see, pressure at bottom, that's the worst spot right there, pressure at the bottom, is going to be equal to the pressure of the air plus specific weight of the water and the height of the water, right? So that's going to be, let's keep it in PSI. So we had 50 plus, and we got to be careful here. I think we want to go 62.4, right? That's pounds per cubic foot times number of feet is going to be 55 feet. Whoop. And so pounds per cubic foot times foot is pounds per square foot. We need 144 inches squared per foot squared, right? 12 squared. 12 times 12. That'll turn that into PSI. We end up getting 73.83 PSI. Okay. So I think we have the loads part done, right? Oh, by the way, in a lot of problems, and I'll repeat this often, what we end up doing, we do some geometry stuff, we do some load stuff, then we do some stresses, and then we combine the stresses. So now we've done some geometry, not just simple geometry things, some load things, found out some loads. Now let's combine the loads together and to find stresses. So I'll write stresses. Just tell what I'm doing. And I'll start with axial. What kind of stress is axial on here? Well, let's not, there is some stuff that will align with the axis, but let's just keep them designated by what we would generally call them, right? Well, for instance, longitudinal stress is in the same direction, but it has its own category, so let's leave it alone. The only axial stress is really going to be from the compression of the weight, right? So it's going to be, let's see if I'll want to give this, I guess I'll write axial. I don't like doing too many subscripts, but it helps. We're going to have F over A. Simple, right? Just the weight of this thing. And like I would say, if you needed to be convinced that this stress was a real thing, think about this thing to be, what if they could just lift it up and you could put your foot underneath it and then they would set it down? Yes, you would know what the axial stress is of this tank, especially 216,000 pounds of it. So we have 2.163 E5, and did I ever calculate the thing out? I don't think I did, but I did. I did it on my my own page. I found out what the area of the wall was. So actually, up here in this thing right here, I did it as a separate step, and so I was able to reuse that step right here. But if we had that right here, we'd go pi over 4, and then we would say that we had 360 square minus 358.5 squared. And what we end up finding, we get 255.5 psi compression. Important to note, it's compression. Now, most of the other stresses are going to be due to the pressure vessel nature of this thing, right? This is a additional load that we have to consider. Now, the longitudinal is a tricky one. Now, you might go and use this pressure right here to find the longitudinal, but you would be wrong. How do I know? How do I know? Well, you see, you're just plugging and chugging. You're not actually thinking your way through if you were to do this. And full disclosure, the first time I did this problem, totally overlooked it. Just was plugging and chugging. It is a trap. Don't fall into the trap. You want to make sure that you're a thinking engineer. So you start to pick apart and say, okay, what is longitudinal stress? Well, longitudinal stress is really the thing that's holding the thing from flying off into space, right? Well, when it comes to our scenario right here, although the pressure, and we could even draw it like a pressure gradient, right? We could say it starts off with a pressure here and then the pressure gets larger, right? So if there's a pressure gradient that we were drawing onto the thing, it would be distributed like that right there. And pressure acts in every direction, but when it's the hydrostatic, it's, we're picking the thing up. It's getting less and less and less and less and less. So at a point down here, you have to think about what are the loads that are really taking place on the steel cross section that we are trying to analyze. And so the pressure, even though that's going outwards, outwards here, I'll go up here, outwards this way, down here at the bottom, it's only the pressure that's on this dome upwards that is really trying to lift this thing up. It's trying to elongate. So when looking at the stress, that we have the longitudinal stress, we should use 50 psi because this 73.83 is going sideways, right? It's not trying to stretch the piece out because it isn't acting in a shear direction. You could even, if you want to draw this thing out, like draw out just the steel by itself, a cross section of it, like this right here, and think about that, right? It's the stresses for the longitudinal stresses is really that stress times the area through the thickness of the thing, and you could think about the loads of the water coming. They're all coming out and pushing out this way, but it's really the pressure of the air that's acting up across this cross section, right? And it doesn't matter that it's a dome. It's just the area that's perpendicular to that upwards direction because this is only in the vertical direction right there. So hopefully you can reconcile that. I hope I've explained it, but if you are confused by it, you might want to argue with it. You might come back and we could talk about it some more. And I totally would like that conversation. So all I need is a subscript L right in there for longitudinal. And it's thin-walled, so I'm just going to use P di divided by 4t. And I end up with 50 times my inside diameter, 358.5, and divided by 4, and then my thickness is 0.75. So what do I get? I get that it's 5,975 psi, and that's going to be in tension because this thing is trying to lift up like a rocket ship and go up into space. So it's the stress that's holding the thing down. So the sum total of my sigma, and I oriented it this way right here. So for my little cube that we would have, all right, in the sigma y direction right there, it's just going to be 5,975 minus 255.5, which ends up being 5,720 psi tension. So that's really the only combined stress type of deal that's going on here. And then so for the hoop, I'll write it as hoop. Or you could have said tangential if you wanted to. I use the subscript T because we're going to say, because it's on the inside surface, we'll get the pressure times the inside diameter plus the thickness, almost said time, plus 2, divided by 2, and divided by t, and so we get 50, and then we get our 358.5 plus our 0.75. It's not going to change it a whole lot. And divided by 4, and divided by 2, sorry, and 0.75, right? And we end up with 17,680 psi, and this is tension, and that's going to be also equal to sigma z. And then lastly, the radial. Sigma r is just going to be negative 73.83. Oop, I made a mistake over here. I'm sorry. This value is correct, but this right here should have been my 73.83. Did I write that wrong? No, I wrote it right on my paper. I just was going through too fast when writing this thing out. That's 73.83 because that's the pressure this thing's feeling down at the bottom of the hoop. That's trying to remember the guy inside the hula hoop. He's pushing the thing outwards, so that's the stress that it feels in that direction. And it also feels the 73.83 in that direction. So if they want the principal stresses, sigma 1 is 17 well, it doesn't really make sense to go to KSI because this one's going to be so small. So we want to definitely represent the thing. So sigma 1 is equal to that right there. That's the largest right there. Sigma 2 is going to be 5,720 psi in tension, and sigma 3 is 73.83 psi compression. And so tau abs max is going to be 17,680 minus 73.83, and it's not really going to change. I mean, this is so much smaller than that right there. But you end up with 8,877 psi, which is what the absolute maximum shear is going to be felt in a stress element that's right here at the bottom of the tank. I like this problem because, you know, it's a long and involved problem, and you got to think your way through it, and it's got a couple of pitfalls that you might fall into if you just start looking at equations and throwing numbers in them. I got to tell you, you want to make the big bucks. You want to get a job as an engineer, and it's really, you're not just going to be any old engineer. You're going to be the engineer that they want on their team. You got to be thinking your way through the thing, and the number one tool that you have to try to make that happen is the free body diagram. That's the tool to get when you have a word problem and it's solid mechanics and you need to try to figure out, is this applicable? What's actually going on right here? The free body diagram is your saving grace. And if you'll find, and experience will show you, you don't have to take my word for it. When you go out into industry and you have some type of problem and you're working through it and some mistake gets made, someone forgot to draw a free body diagram. And when people are trying to figure out the mistake, they're going to be drawing free body diagrams to figure it out. Live it, love it, use it. All right, enough preaching. Let's make another video. How long was this one? 23 minutes, 24 minutes. Wow.